I'm sharing today is the model execution and the system simulation in Capella, which is the same with the one I have talked about on the Capella Day last month. And um, for today, we have more time, so maybe we can talk into some details. And the first part is the background and the motivation. The second part is the execution and the simulation rules, and then some examples. Glaway has been deploying Capella-based MBSE solution in Radar Institute since late 2016, and in this institute we have done some extensions based on the Capella, and we have some kind of private solution MBSE modeling tools in this institute, and we call it SMAX. That means system modeling experience, and later we will see it. And the radar products from this institute vary from seeker, spaceborne, airborne, shipborne to ground-based, many products. And by now, each product area in this institute has at least one product using Capella-based solution in its architecture design, and including the most complex one. And this year, we are trying to to link the DEF modeling with the system modeling, then from the system modeling to different domains. For example, the electronic design, the 3 dimension design, and some other disciplines. So we are trying to make the design information flow along the from the SOS to the S and to the different disciplines, and Capella is the center of the design tools, all these design tools. And during the deploying of Capella-based solution, one of the biggest challenges is how to verify the architecture design is correct. For example, if the mode and state machine is consistent with the scenarios, and if the functional decomposition is correct, because in this institute we are mainly designing radar, so we need to know if the algorithm we designed we choose can get the most desirable result. So we need some extensions based on the Capella. So our solution is to develop an add-on to make the state machine executable, and we can use a control panel to interact with the state machine and record the execution process automatically as a scenario. So before the execution, we can manually draw a scenario to stand for our requirements. Then we can execute the model, then get some scenario that is generated automatically, then compare these two scenarios to find out if the requirement is satisfied. And during the state machine execution, if we have some MATLAB code or C code embedded in the functions, we can also invoke them to simulate the operation effect of the architecture. Then I will introduce the execution and the simulation rules. We have two types of execution rules. The first one is state machine rules, and the second one is functional data flow rules. And I will introduce them one by one. And that's the first one, state machine rules. It is based on Mealy machine, and we can use triggers to trigger the transition between states or modes. And the triggers can only be functional exchange or time event. And we also have the guards of the transition, which can directly reference the property values from relative components. And different state machines can use jam mechanism to trigger each other. So in the state machine rules, the functional exchange and the triggers, they are independent. They are independent mechanisms. So the functional exchange only stands for the input and output of different functions, and the triggers, only the triggers can trigger the transition between different modes or states. So the triggers are sended by hand or by the jam mechanism, and it's not it's not the same as the data input and the data output. So we have done some extensions on the attributes of the modes and the transitions. We have several gens, the entry gen, the activity gen, the exit gen, which means we can gen some triggers when we enter some modes, and we can, for example, gen some triggers when we exit these modes, and we can gen some triggers when we're doing the transition. And this slide will show the exact rules, the exact sequence of all these functions or gen triggers. And for example, at the very beginning, we will enter the mode 1. Then we will execute the do function of the pre-state. That means that the mode 1. Then we will generate the do gen trigger of the pre-state. Then a trigger arrives that will trigger this transition. And the guard is satisfied. The transition will only be done when the guards are satisfied, and the guard can reference property value directly. Then we will exit the pre-state and execute the exit function of the pre-state. We will generate exit gen triggers of the pre-state. Then we will execute the effect function of the transition and generate the effect gen trigger of the transition. Then we will enter the post state and execute the entry function of the post state and generate the entry gen trigger of the post state. And we can see we also have the time trigger. So this is similar to the state machine of SysML. And the second part is the and this is the display rules of the state machine execution. And the current state will be highlighted by red. So in this picture, in this slide, the mode 4 is the current state, and the transition to the current state will be highlighted by yellow. So this transition is highlighted by yellow. That means for this state machine, mode 3 is the pre-state, and the functional exchange 2 is the entering trigger, then trigger the state machine transmit from mode 3 to mode 4, and now the current state is mode 4. So this is the transition to current state. And the states or modes and the transitions that have been through are highlighted by green. So Mode 1, Mode 3, they are green, and this transition is highlighted by green. That means in the execution of this state machine, we have been through mode 1, this transition, and mode 3. Then we come to mode 4. And the state name modes and transitions that have not been through will display as default. So that means in the execution of this state machine, the functional exchange 3, this transition, have not been through. And the process of the execution will be recorded as scenarios automatically. And during the execution of the state machine, we can use a control panel to interact with the state machine. So we can select the target to send the triggers. We can select the triggers to be sent, and we can define the value of the triggers. So this value means the value of the functional exchange that stands for the triggers. So it is only be used when the function has some embedded codes, for example, the MATLAB codes. And this area will record the history of triggers that have been sent. Okay, now comes to the second part of the functional data flow rules. And this is based on PatriNet, and we will see it is similar to the activity diagram of SysML. And we have added one more modeling element that is the initial node, this one. And we can see this example. The function connected to the initial node will be executed at the very beginning of the execution. Then on each output port of the function, we will generate one token. And the token will travel along the functional exchange from the output port to the input port, and it will take no time. So it will travel along this line, this edge, very fast. And then for this function, the logical function 4, on each input port of this function, we have one token because it only has one input port. So it will be executed next. And for logical function 5, because we have two input ports here and we only have one token, and on this port we don't have any token, so it won't be executed. So for each function, only all the input ports have at least one token, and then this will be executed. So we will execute this next. Then after the execution, we will consume one token on each input port, then generate a new token on each output port. Then the token will travel functional exchange to the input port very fast. Then the logical function 5, it have enough tokens, then it will be executed and consume these two tokens. So this is the main rules of the functional data flow execution. And in our add-on, we can also make these two rules to make a hybrid execution together. For example, we got two logical components, and one with a state machine and one without a state machine. Then this one, the logical component 1, will execute under the state machine rule, and the logical component 2 will be executed under the functional data flow rule. And the component with the state machine will have a little mark on the right up corner. And we can open the state machine by the right-click menu. And on the edge, on the border between the state machine role and the function data flow role, we will use the token and the triggers to interact with each other. So the token will be equal to the triggers on the border. For example, after the execution of logical function 2 here, it will generate 3 tokens. Each token is on one output port. Then this token will be transmitted to the logical component 1, and it will act as a trigger. It will act as a trigger in the state machine. And in this state machine, we can use chain mechanism to generate some triggers to other state machine or other components, and these triggers will act as a token on the border. So this trigger means we will generate one token on this functional exchange, and the logical function 7 will be executed with this token. Then I will introduce the how to embed MATLAB data, MATLAB code in the functions. We can invoke MATLAB editor to edit the embedded code by right-click menu. For example, on the menu, we will got the edit code with MATLAB. Then it will open the editor of MATLAB, and in the editor, the first line of the MATLAB function will be auto-generated. It will reuse the function name, so the function name will be equal to the function name in SMAX, the function name in Capella. And the input and output parameter in the MATLAB function, it will be equal to the input port name and output port name in the Capella. And we will also have local data here, both in the input and output. And this is for the reference of the property value of relative component. So we can use local data dot the property value name to reference to the property value in Capella. And also we can add breakpoints to do some debug. And sometimes, especially in the execution for a real radar system, the functions invoked and the functional exchange invoked will be very large. The number of the functions invoked will be very large. So it will be impossible to highlight the transition of different states and modes and record the scenarios and update scenarios in real time. So we develop display options here to improve the execution efficiency in some cases. So we can choose if we insert the scenario at real time, and if we update the scenario at real time, and if we highlight the state machine at real time. And if we are not insert and update the scenarios at real time, then we can choose to insert these all these elements at once after the execution. And if the simulation is too complicated, then we can also choose the last one to record the execution process in text in a XML file. So if we check this one, then during the execution, we won't see the highlight of the state machine. We won't see the update of the scenario, and all the process will be recorded in XML files. Then after the execution, and we can replay the process by hand. We will show that later. Then comes to the example. And I can show you some simple example first. Let's do this one. And this is the modeling tool we are using in the Radar Institute. So all these are translated into Chinese. For example, we have two logical components here, and this one have a state machine. And we can open it by right-click menu. And this is the state machine. And we got some entry chain. This is added here. Entry chain. And this one, logical component 2. It is not. It does not have a state machine. So initial node. Then we can execute it. Because this is a simple example, so we can insert it at real time, update it at real time, and highlight it at real time. So we can see this is the record of the scenario, and this is the highlight of the same machine. And now it is on the mode 4, and it is transit from mode 3, and this two has been gone through. And we have a plot here, and this plot comes from the logical function 7, because we can look at the code here. So it have some plot. And you can see another example. And in this example, we have two logical components. They all have state machine. In the first state machine, it will enter mode 1 at first. Then when functional exchange 1, when this trigger comes, that is this one. When this comes, it will execute the logical function 2. It will execute this. Then it will generate a trigger to another state machine. So it will generate this trigger to this state machine. And the functional exchange 2, the trigger here will trigger the transition from mode 1 to mode 2 and execute logical function 3. This execute this one. Then after 2 seconds, it will get back to the mode 1 and generate a trigger functional exchange 3 to the first state machine, which will trigger this one from this transition, and it will generate another trigger, that is this trigger, back to the logical actor. So this will show the interaction between two state machines. This is the first one. This is the second one. Then we can generate a trigger by the control panel and generate a functional exchange 1. And yeah. Okay. So each state machine have been through all the transitions and all the modes, and for the scenario here, you can see it comes from the logical actor 1, then to logical component 2, then after 2 seconds, it's get back to the logical component 1 and get back to logical actor. So it's the logic is consistent with the model here. And we can see another simple example here. And this example have some simple meanings. We have an actor, a controller, and an engine. And the actor will send the control instruction, send some command to the controller, and it will pass the instruction and give start signal or end signal to the engine. And in this function, we will pass the instruction. That means if the input is 1, then we will store the input in is start in this property value, and this is here is start. And if the input is not 1, it will set the is start to 0. So this is the example how to reference the local data here. Then in this state machine, after passing the instruction, it will make a choice, make a judgment, and based on the is start. This will reference to the property value 2. So if this is start is 1, then it will send the start signal, and if the is start is 0, it will send the end signal. And for the state machine of the engine, it will be started if it get the start signal, or it will be ended if they get the end signal. And it will get back to the down state after 20 seconds without any signal. Not this one. These two scenarios, they are the same. So to the controller, we can send a control instruction, and we can set different values. For example, value 1. It will get the engine started. And if we send value 2, it will shut down the engine. And if we start the engine and wait 20 seconds, it will shut down. It will shut down. It will be shut down because of the time event. So this is the record automatically generated. Okay. All these are simple examples, and now we can get to a little complicated example. And this is the MPAR example I have shown on the Capella day. It is a multifunctional phased array radar based which perform both scanning and tracking tasks. And most of its simulation codes comes from MPAR search track example in MATLAB 2019A. And this example intends to show how to use execution add-on to do system simulation, and it's not about how to design a real radar. And this picture comes from MATLAB 2019A too. And in this example, we have 5 subsystems: the radar managing subsystem, the antenna subsystem, the signal processing subsystem, the data processing subsystem, and display subsystem. And it will be controlled by a simulation configurator and a simulation controller. The configurator, it will mainly update the simulation time. And we only have one real target here, one real actor here, that is the target. And only the antenna subsystem and the radar managing subsystem has state machine, and these two subsystems does not have any state machine. And this is the state machine of the simulation configurator. The main function of this state machine is to do some initialization of the simulation and send some send initialization signals to different subsystems and an update time for each dwell. This is the state machine of the radar managing subsystem. After the initialization, it will get the current job on the start of each dwell, and based on the type of the job, it will judge if it is it's a search job, a track job, or a confirm job. Then it will send the job type to different functions and calculate the beam direction based on the job information, and send the beam direction to different subsystems. And this is the state machine of antenna subsystem. And it will get into the transmitting mode and the receiving mode for each pulse, and it will make a loop here until all the pulses has been transmitted in one dwell. Then after that, it will get back to the standby mode, and for the next dwell, it will come into the transmitting, receiving, and after all pulses are transmitted, it will get back to the standby. And after the dwell is ended, it will send all these signals received to the data processing, to the signal processing subsystem. And all functions in this example has some MATLAB codes embedded there, and these are some examples. And this is the video of the execution, and I will show it live. This is the NPAR. We have the data managing, antenna, signal processing, data processing, and the simulation configurator. And we can take a look at this here. In the state machine of an antenna, it will transmit and receive for each pulse, and it will on the entry function, it will invoke the transmit function. Then it will use an entry chain to generate a trigger of the FE wave. So that means it will invoke this function. It will invoke this function, the transmit function, and generate a trigger of EV wave. And this will comes to the target. And for target, it does not have any state machine, so it will be executed under the function data flow rule. So the trigger generated from the transmit, it will act as a token to the generate echo. So there will be a token here because it only has one input port, so it will be executed when it got the token. Then it will generate a token here as the FE echo, and the token generated here, it will act as a trigger to the state machine. So you can look at here the FE echo. It is a trigger. It will be triggered here, and the state machine will transmit transit from transmitting to receiving, and receive the echo and do the pulse integrate. We can take a look at other state machine. State machine. By the way, we can also create a state machine by the right-click menu. We have done that, and it's quite convenient. And we have different functions, different code here. We won't take into the details of the code. Let's execute that. Because it will invoke many functions many times, so we won't doing the highlight and the update at real time. We will put all the information into the XML file after the execution. The start of the simulation is the start signal is the start order. This is generated by the display subsystem. It will show the beam here, and there are two targets here, the little triangle here. And when the beam touches the target, it will transmit a confirmed beam. The orange one is search beam, and the yellow one is confirmed beam. When it's confirmed, then it will the purple is track beam. It will use some track beam to get the track of the target. So these two plot here stands for the tracks of the targets, and the targets it's moving. They are moving. And we can wait several seconds to see. This is the track of the target. This is the track of the target. So in this way, we can simulate if the effect or if the result of the algorithm designed here and the functional architecture designed here is desirable. And the target information are set in the simulation configurator, in the functions on the configurator. So we can try 2 targets, 3 targets, 4 targets, for example, and we can set the velocity, the position of the different targets, and do some experiment here to test the algorithm and the architecture we designed in our radar. Okay. And this. And now we can replay the scenario by input the XML file here. So this one is generated right now, and it has 14,000 nodes here. So if we insert all these nodes into the scenario, it will be very slowly. So we only enter, for example, 50 nodes here. Let's update the diagram. You can see how it is worked. That's the MPR example. And I have some interesting point here I want to share with you. The first one is the n-square diagram. We have done some little extensions here to generate the n-square diagram. For example, we got 3 logical components here with some functions and function exchange. and we can generate a n-square diagram based on this model. This is generated right now, and you see. This is the logical component, and this 118427. This stands for the functional exchange. We have for each functional exchange, we have an ID here. So it will be marked on the n-square diagram. And also another one is, I remember on the Capella day, the Pharmaton has shared their what they have done in their company, and there is one challenge that I remember is how to share all the how to share the new version of the modeling tool over the company. So for that one, we have a little feature in our extension that is an update online. So for each engineer, we can check if we have new patches on the server. So we can use this one to check the update. Then if we have updates, if we have patches, it will be updated automatically. So we have done that. It's an interesting point here. Okay, that's all I want to share with you tonight. Okay, so
we have a few questions. I will send it by email. You will receive it.
Okay. Does the executable Capella has been developed using gmock? And no, it's not. It's not using gmock. I don't think we are using any open source tools or architectures here. As history state is also considered during execution. As history state is also considered during execution. History states will not be considered during execution, I think. I'm not sure if I have understand this question, but when we are in the execution of the system machine, the next step will only be based on the current state and the triggers incoming. So the execution of the next step of the system machine, it won't consider the history state. Is it possible to embed C code from external sources? And we have do some experiment. We have done some features on the experiment. For example, on the preference, we have the choice here, the MATLAB or C. So we can also embed C codes in the in the functions, and in the similar way of like MATLAB codes. But this is not very mature, and MATLAB is more mature. It seems that all functional exchanges are considered to be discrete on a trigger. Did you investigate functional exchange that could be continuous? Actually, I think in the state machine rules, we have treated the trigger and the input and output separately. So the triggers, they are discrete, and the input and output, they can be continuous. For example, in the radar example, the wave and echo, they can all be considered continuous, at least in a very short time. But yes, we don't have any special design for the continuous exchange. And the next question, does the time event are also recorded in the scenario as a kind of duration constraint? I think in some example before, I have shown how we record the time event. It will be recorded like that. Can you generate the final deployable code from models? If not, are you planning to add such capability? Yes, we are trying to do that. So we can see right beside the execution button, we have an code generation button. So by click that, we are supposed to generate all the M files for each function, and we will generate a main function of the machines, also in MATLAB. So after clicking this button, we should have a set of M files, and most of the M files are from the embedded code, and one big M file which will be named the main function, that will stand for the control logic from the state machine or the function data flow, and this function is still under development. It's not finished. And do you have any plans to share or open source your extensions? These extensions, maybe this won't be an open source. It will be a commercial add-on, and by now it has not been released officially, because it is embedded in the modeling tool right now for our for the customer, the Radar Institute. So we will spend some time to encapsulate this add-on and translate some Chinese into English, and doing some extra work. So our initial plan is to release this add-on by the end of this year, and maybe we will modify the plan based on the requirements from, for example, from Europe. And if we have many requirements, then maybe we will make it fast. But if we don't have much requirement, maybe we will just let it embedded in the model, embedded in the modeling tool, and just use it in this radar institute. Where do you get real time for simulation? Is it from Windows? Yes, it's from the operational system. Yes, the answer is. And since the add-on uses MATLAB embedded code for behavior support, does the Capella modeling supplement or maybe replace similar design verification in the MATLAB tool? I think in some, yeah, we can say that this add-on can replace the Simulink in at least some feature of the Simulink in MATLAB. In this radar institute in China, the engineers there, they thought Simulink is not so so easy to use. It's very slow, and the state machine is not very easy to understand. So they prefer to use the feature we developed in Capella, and so yes, we can say it can replace similar features in Simulink. But maybe for other customers, they thought Simulink is more easy to use. So that will depend. Is this application available in English? Not by now. We when it is officially released, it will be in English. Of course, it's not. It only has the Chinese version by right now.
We have another question. I'm sorry.
And your extensions appear to offer similar functionality to Simulink. Do you find that Capella is sufficient for your needs? And at least for our customers of this Radar Institute, the answer is yes. And because in Simulink, we don't have the operational operational analysis, the system analysis, the logical architecture, and the physical architecture. So the Capella is more, it's they have more model elements to help engineers to do the design work, and the state machine feature in our extension is more easy to use than the Simulink. So for them, Capella is sufficient. There are open source alternatives to MATLAB. Have you considered using these instead? The answer is at least no by now. I don't know. Maybe we will consider the Octave in the future. We doesn't have we don't have any plan here now. Okay.
There is one last question that I received by the chat section. Do you want to share these developments with the Capella community, or what is your economical model behind?
And so, do we plan to share this add-on? You mean? And I have, I think I have answered a similar questions before. So, um, it will depends on the requirement. If the requirement is, for example, many companies are interesting, and then we will spend some resources to encapsulate that and translate that and get it make it available in the in the Capella environment, and if the requirement is not so strong, then it will be done later. So our current plan is to release this add-on at the end of this year.
Okay. Thank you very much, Renfel, for this really interesting webinar. Thank you everyone for your participation and the question you asked. Feel free to answer to the survey. We will send it just after the webinar, and we will keep in touch, and we'll organize a webinar next month. So stay tuned. Follow us on the social media, LinkedIn accounts, and etc. Feel free to ask if you have any question. Thank you, everyone. Thank you, Renfel, again.
You're welcome.